one slide. It's physical copy.
So I'm going to close the door.
Unless you want to take a picture of it. Yeah?
I'll like watch the video anyways, but
it was mainly like a conversation.
Yeah, I saw the video a little bit.
Okay.
Well, I have to wait until the
That's why I'm waiting.
Better days. So I take notes on my computer.
You need an iron.
There you go.
So, good afternoon. So this is part 5 of the promise and perils of AI. As a segue from what you saw with Rich, and I'm speculating what you saw with Rich because I wasn't here, but I know him well enough that I will actually dare to give you my definition of human intelligence. I'm sure he talked about his definition of intelligence. So for me, human intelligence is basically the creation of tools to extend our capabilities and prevail. Whether it is a language, or a hammer, or AI per se. Okay, so AI is also a tool. So I see it as basically assistive technology to help us do things things better than what we do normally, and prevail in nature, in our universe that we live in. If computers, or whatever technology, starts also creating these tools to prevail, then we can talk about the singularity, because they will have means to improve themselves. They create tools to assist themselves and improve what they can do, then we can talk about singularity. So, part 1 and part 2, that's what I presented in the past, so I'm reminding you a little bit what we talked about. We talked about the promise and perils of AI in general. So what is a thinking machine? We talked about singularity and big data. And in that lecture, I was mentioning the fact that we shouldn't be arrogant to believe that we are the top of the chain in terms of intelligence. Yes, we can imagine things that are animals or whatever, entities that are less intelligent than us, like a mouse, like a cockroach, whatever. But we should accept the fact that there are other possibilities of intelligence that are superior to us. That could be a machine one day. If the machine, as I said, starts creating these tools to extend its own capabilities and prevail, then we have this singularity. And I mentioned that there are many paths, according to me, to this singularity. First path is evolution. We will help evolution to select the people that are the smartest, and then the average maybe will go up. It's unethical, but technically it is feasible, but it'll take a long time. So probably not the best path. The second path is the path that most people talk about, is this strong AI, so an AI that will be more intelligent than us. I more believe in the third path. The third path is the path that I call the cyborgs. So these are other tools that we add to ourselves as the human body. So arms, eyes, extensions to memory, or who knows what. Okay. And the fourth path is this Internet of Things. So having many intelligent pieces connected together may create the emergence of a new kind of intelligence that we don't know about today. That doesn't mean that these are the only paths. A combination is also possible. We shall see. So we also talked about some achievements in AI. Again, AI today is just an assistive technology that we're using, and we used it to do many amazing tasks, and we achieved incredible feats, typically in games, but also we talked about self-driving cars and so forth. And we're doing more and more of those. So today what I'll be talking about is machine learning. How does a machine learn? When we talked about intelligence, we also talked about this capability of learning from the environment. We humans can learn. We're not the only ones. Animals can learn. Okay? Can machine learn? Yes, but how? That's what we'll be talking about today. Okay? Some of the achievements of AI that I talked about are old. They're not new. And that's because AI has been around for a long time. I talked about the history of AI, and we went through two winters. Now there's an emergence of, AI is coming back in the media. Everybody's talking about AI. Why? Why now? What's happening? So before I start talking about machine learning, I wanted to mention this. Well, the resurgence of AI is due to three factors that are happening together at the same time. First thing is that today we have a lot of data, more data than we have ever had before. Okay? And this data is available, particularly to huge companies that are collecting information about you. But at the same time, our computers had, we talked about this Moore's law, they improved significantly. And today you can buy a GPU on your desktop at home, and it's as powerful as Cray 1 a few years ago. And it's $1,000, while a Cray 1 is hundreds of thousands of dollars. Okay, so these are available. But the third factor is the development of new, very powerful algorithms. Among them, what we call deep learning. Have you heard of deep learning? Yeah. Okay. So deep learning is becoming, part of the vocabulary that most people are using. Yeah, you have a question.
Yeah, I was just going to. It was awesome that you brought that up. Is that was that the neural networking breakthrough that they got from neuroscience?
I'll be talking about deep learning. What is deep learning? The problem is that people are talking about deep learning without knowing what it is, and it's becoming a synonym of AI, but it's not. AI is way more than just deep learning. But I'll mention what deep learning is and why it is in everybody's mouth, basically. Deep learning is indeed part of neural networks, and it is machine learning, and that's what we'll be talking about today, machine learning. Okay. But what you should remember is that deep learning is not AI. AI is not deep learning. Deep learning is part of AI. AI is way bigger than that. I took this quote from an article in the Wired magazine. You need AI researchers to build a smart machine, but you need machine learning experts to make them truly intelligent. So what are these machine learning experts, and what is machine learning? Well, if you look at Wikipedia, machine learning is a scientific discipline. They deal with designing and developing algorithms that allow a computer somehow to change the behavior given different data. Okay. So what we have these algorithms or programs that provide means to the computers to learn from data, interpret the data, and then adapt to the data as it changes. So basically you have data coming from the world, and that's the experience. You learn from it, and then you use what you learned, the model that you learned, to adapt to the environment as it changes. Okay. It's close to what Rich Sutton was talking about, this robot moving. Like the agent in a maze, and you change the maze, it adapts to it again and again. Okay? So basically, it's about learning from experience, and you adapt to the environment based on the model that you learned. And we'll talk about that in detail. Okay? So let's see some examples. The best way is to focus on examples and understand it by analogy. So if you take the program in accounting, you have millions of lines of code. Okay? A company A can use it, and then a company B can use it. And these two companies are different. Maybe that's the program that adapts from one company to the other. Well, all the complications that exist here, they're just rules. Rules in accounting that a programmer will code inside the software. If you have this case, then it should be this. If you have that, then it should be that. It doesn't really adapt. All the rules are written the same way for this company as they are written for this company. Okay? So it's not really machine learning. Let's look at the other case. You have a large database with a lot of data, and then you query it, and boom, you get an answer. You change the query, boom, you get another answer. Is that machine learning? No. You express the information need that you have in a language, a query language, and there is a processor that understands that query, does some analysis of the syntax to see if it's correct or not, and then converts it to some calls to different tables, different indices, and voila, you get your answer. It doesn't really adapt. You change the query, you express it differently, so there's no adaptation. Let's take a robot. Maybe robots adapt. So if I take the example of a robot in a manufacturing plant, I'm building cars, and I build different models of cars. I build small cars and big cars. But when I'm building the small car, I will tell the robot to go to this X, Y, Z coordinates and put this particular pressure, this temperature, whatever, and do it again, do it again, do it again. If I change the model, I have to change the coordinates and go to a different place. That's not really adaptation. I'm hard coding the X, Y, Z coordinates each time. So all these are not machine learning. So what is machine learning then? Well, here are some examples. I want to build a program that can help a doctor analyze medical images, saying, here's a region of interest. I cannot conceivably tell the program, here are all the possibilities. It's infinite. I cannot code them all. It's like the rules in accounting, for example. Every single image is different. So in this case, I have to provide a set of images where I say, this is a region of interest, this is a region of interest, and so forth. And then the program will learn from these examples. And then when I give another image that hasn't been seen before, it'll tell me, oh, I learned from the others. That's a region of interest now. So now the program is adapting, learning from examples, and now changing the behavior with the environment. The environment now is a new image that is coming to it. Okay? So that seems to be machine learning. Another example, filtering data for analytics. I don't know exactly the data that you want. And I have a fire hose of data coming from the news, the tweets, whatever, you name it. I will observe you, what you like and what you don't like, what you share, what you comment on. And then I learn from that a model that represents you. And then automatically filter the data as it's coming to you. I know that this data you will not be interested in, so I dump it. This one, oh, I think you will share it, you will comment on, and so forth, and then I'll show that to you. And I'll adapt to you. And I'll do something different to somebody else. So that's machine learning. I learn. Okay? I cannot code every single person in my code. There's no way. Is there another example with a robot? I'm building a robot, sending it to another planet. I have no idea how that planet is. I haven't been there. It's not just sending it to Mars or elsewhere. Even here, I'm sending it to a building that collapsed to see if there are people there and I want to rescue them. I don't have the map of the building anymore. The building collapsed. So I need the robot to adapt to that new environment. So it learns to change behavior in a simulated way, and then I send it to an environment where it's new, and it'll adapt to it. Does it make sense? So these are machine learning. These are not. So it gives you a little bit a flavor of what we're talking about. There are many kinds of machine learning. There's what we call supervised machine learning, and most of the examples I showed you are supervised machine learning. So supervised is because I give it a set of data that has been annotated. I'll tell it, this is interesting, this is not interesting, this is interesting, this is not interesting. And it learns from that. This unsupervised learning where I say nothing. And it learns how to well, we call it learning because it's actually classifying the data into groups without me telling it how many groups there are and which groups I'm interested in. There's semi-supervised learning where you have a mixture. Active learning where you have a little bit of labeled data, and then as you're labeling new data, you take advantage of that to improve your, when it's correct, you improve your model. There's what we call reinforcement learning. I don't know if Rich talked a little bit about that. That's his specialty. He's one of the pioneers of reinforcement learning. It's very similar to how a child behaves or a dog behaves when we're trying to teach it a trick. Okay? So why? It's because they have a set of actions that they can do, and they have to choose one action, and if they choose the right one, here's a treat. If they don't choose the right one, I don't give a treat, or even a penalty. Don't do that. Oh, that's great. I give them a reward. We call it a reward. So basically what you have in reinforcement learning, you have an agent, you have an environment, and the agent has a set of actions it can do. Like a robot, it can turn this way, can turn this way, can go forward, and so forth. And then it chooses an action, one of the actions that it can do, and by choosing an action, it changes the environment. So there is an observer, an interpreter, that will tell it, here's the new state of the environment changes due to this action, and here's a reward. And basically the agent is trying to maximize the reward. Like the dog wants another treat, give me another treat, until finally it ends up rolling or giving the leg or something like that, or the child starts doing the right thing that we want it to do. Okay? So the agent is just trying to maximize the reward. There's negative reward and there's positive reward. That's what reinforcement learning is. I'm reinforcing it, reinforcing the learning based on this reward. There's also transfer learning. You may learn something in a world, you move to another world, how you transfer what you learned there and apply it here. So the data changes, for example, and so forth. But we will focus on supervised learning. I cannot cover all these, but we'll focus on supervised learning. And you'd be surprised. You're using today things that are built on this supervised learning without you knowing. It's actually very common today. I'll show you examples. So how does it work? Imagine I have a child here sitting next to me, and I have these buckets, and I have a pile of balls, different sizes, different colors, different textures. And I tell the child, okay, watch me and learn. Watch me what? Well, I'm taking one ball, and I'll put it in a bucket. And the task of the child is to learn which ball goes to which bucket. So I take the ball, I don't say anything, I look at it, put it in the bucket. After a while, the child watching me will build a model, deciding is it the weight, is it the color, is it the texture, is it the size of the ball that makes me decide in which bucket to put it in. And they will build a model, and then at one point I'll say, okay, it's your turn. I give him or her the ball and say, now put it in the bucket. They will use that model, their belief of what I was doing, and then put it in the right bucket or the wrong bucket. If it's in the right bucket, they learned. They didn't do it in they didn't put it in the right bucket, then they didn't learn enough, then I have to continue to do it. Make sense? Okay. This is what we call classification. So I'm classifying, because I'm putting this data record in a class, the bucket. Typically, I know how many classes I have. It's an n, it's a finite number. Often it's just 2. For example, this is interesting information, this is not interesting information, I don't show it to you. Okay? This is interesting information, I'll show it to you. I'm trying to adapt to you. Okay? And the child seeing me doing this task is learning based on a training data. So this is data that has been labeled because I put it in the right bucket. Okay? So here's another example. I have data that we call training data. It is labeled, so in this case I put colors to represent the label. And I have data that hasn't been labeled, so it hasn't been seen before. So I'll take the training data and I'll process it. That's representing the algorithm processing it. And I will build a model. That model can be, I don't know, a special data structure like a neural network with weights and stuff like that. It can be a formula, it can be a set of rules, a hyperplane crossing the space, whatever. Let's make it more friendlier. So put a face. Now that I have that model, that's what I learned. I'm going to use it to label those that I haven't labeled before, that haven't been labeled by anybody. Boom. And I label them. That's what classification is about. Okay? This is the learning. This is the use of the model that I learned. Okay? Now, it's not just that. There are many complications, of course. There are many challenges. When I'm taking this data that has been labeled, what are the features that are relevant to decide which class they should be in? Like the child looking at me, taking the ball and looking at the ball and putting it in the bucket, they have to decide, is the weight important? Is the color important? Is the structure important? Is the size of the ball important? These are features. They're variables. Some are relevant, some are irrelevant. Okay, so what are the relevant features? It's not a trivial task to do. Sometimes you have to engineer new features. How to build the algorithm that goes through that and efficiently and effectively finding these features and classifying, so building the model is not trivial, it's a challenge. And there are many algorithms, and I'll talk about 3 classes of these algorithms. How to represent this knowledge is a challenge too. And then how to use this challenge, this model afterwards to classify properly is also a challenge. So there's a lot of challenges that people are still working on. Not all algorithms work in all conditions. There are some conditions where you have to devise a new algorithm and so forth. Okay. There are other concepts that are very important in machine learning. Often you have a case where you have data and you have many classes. So you need to build a model that represents many classes at the same time. Like the many buckets for the child. I presented many buckets. And many applications, you have only 2 cases. For example, you want to detect spam or non-spam in your email. Or this image has cancer or doesn't have cancer. There are 2 cases, one or the other. And then when you build the model only looks at 2 classes. Okay? And these are 2 different kinds of problems. This is definitely more challenging than the first one. You can also use the second model to create a cascade of this against the others, this against the others, and so forth. But anyways, there are 2 kinds of classification problems. This is called multiclass. This is binary class classification. Also, when you're using your model to label things that haven't been labeled before, there's the case where every single one receives 1 label. Every ball goes in only 1 bucket. Okay? This is called single label classification. But there are other cases where actually each object can be labeled more than just 1 label. For example, here you have medical images, and you want to say what type of cancer is there in this medical image. Well, in one image you may have more than just 1 type. Okay? Or in this image you have animals and you want to recognize the animals. This one has a dog, this one has a cat, this one has a camel or whatever. Well, some images have both. Okay? So you may label them more than just 1 label. This is called multi-label classification. There are other things. This is extremely important, particularly in medicine. And now it's becoming a new subfield in AI called explainable AI. So when you have a training data and you have your algorithm going over it, it creates a model. Often, and I said the model can be many different things. Well, many models, this is the cloud that I represented before, many models are black boxes. It learns perfectly but you can't open that box and see what is that model. While other techniques, when you learn and you build, you build the model is transparent. So transparent means that you can interpret it as a human being. Here, for example, there are rules. A and B implies this class. C and D implies this class. I can read it. Not only I can read it, but if I'm an expert in the domain, I may say, yeah, this represents part of the knowledge. I know more than what is expressed in that training data. There are things that are not in that training data, and I can inject that knowledge in here. I wouldn't be able to do it in the black box. Why this is important? Because in medical applications, if you build this to have a decision support system for the doctor, and if it's a black box and it's perfect, 99.99% it's correct, well, the physician cannot ask that black box, why do you recommend this and not that? Okay? And that's problematic, because the doctor has to take responsibility for the decisions they make. In here, you can ask it, why do you recommend this or that? It'll tell you, oh, I'll use these rules, and these rules are human readable. Okay? Make sense? Another very important case in machine learning is it's the problem of unbalanced data. So remember, we talked about data is labeled first, you provide that for training, and I build the model based on that. The assumption is, if I have two classes, the assumption is that I have representation from both classes the same size. Okay? So I have as many green as red, and I build a classification model. For example, these are the sick people, these are the not sick people. But in reality, in most cases, I have an imbalance. If I go to the doctor of an oncologist, the majority of the patients referred to them, they have cancer. Those who don't have cancer are small, because they were already pre-filtered. If I go to a place where they do screening, it's the opposite. Most people are fine, only a few have cancer. So it's always imbalanced. And when you have an imbalance, what happens is that the model learned is biased towards the majority class. Okay? And that's the case here. I have an imbalance. I have more green than red. And what happens is that I will create a model, but that model is imbalanced. Okay? Make sense? So we have to always think about these cases, particularly that they're very common. That's utopia. That's reality. Okay? And most techniques assume that. So here's some examples that you're using today and you don't even know. They are using actually machine learning to solve these problems. A spam detection. Using an email client. That email client is observing you, what you delete, and what you read and answer, and will learn from your behavior what is spam for you, because what is spam for you may not be spam for somebody else, and vice versa. Okay, so it adapts to you. And that's what they do today. Credit approval. You go to the bank, you ask for a loan. They will look at your record. And they already learned from a set of data that they had, the previous customers that they have, who pays back, who doesn't pay the loan, and then they will learn from that to decide whether they'll give you the loan or not. Okay? Suspicious credit card transactions. They learn from past behavior, what you paid, what you bought, and stuff like that. And then when you buy something new and you ask for authorization, when the store is asking for authorization from the credit card company, they check if that, with machine learning, whether that transaction is legit or suspicious. Okay? So typically what you have, this is the framework, you have data that is labeled. It is split into two parts. One part is used for training, and I learn a model, that's my cloud here. And then that part that I left aside is also labeled. I will hide the labels, and I use my model, I'll go back here. I'll use my model and I will estimate the accuracy by comparing what the model is predicting and what are the real labels that I hit. Okay. If my accuracy is acceptable, then I can deploy it. And deploying it means now I can use unlabeled data and then I will label them. If that accuracy is not acceptable, I will train again with different data or different algorithm and so forth. Okay. So most of the techniques use the same kind of idea of holding out some to do a test, and there are many techniques for holding out, and and you iterate like that. So there's what we call K-nearest neighbors, decision tree induction, neural networks, as you mentioned, Bayesian classifiers, associative classifiers, support vector machines, case-based reasoning, and so forth. I'm not going to cover them all. I'll just to give you an idea about how completely different techniques are actually doing exactly the same thing, or reaching the same goal. I'll talk about K-nearest neighbors, decision trees, and neural networks. And they do exactly the same thing. You have data that is labeled, and the ultimate goal is to give you a model that will help you decide for new data that hasn't been labeled before. Okay. So nearest neighbors. Nearest neighbors is the simplest technique. We use it. Doctors use it unconsciously. We call it lazy learning because actually we're not learning anything. What happens is that I have training data. I don't even look at it. I just sort it somehow and I leave it on the side. When I have a new entry that hasn't been labeled, I will look in my cases that I have here, the nearest neighbor. Who's the closest to it? And I'll take the label of that closest neighbor and I'll attach it to the new entry. Okay, so basically here's the data that I have. I have gray and green. Have a new object coming in. Then I search based on some distance function, the similarity between records. Which record is the closest to this one? Oh, it's this guy. It's green. So this new one should be green. Okay? So I'm a doctor, for example. I have this patient coming in and he has some symptoms. I look at my records. Another patient has similar kind of symptoms, similar kind of characteristics. I gave this treatment and it worked. I'll give this treatment. Make sense? Okay. Using just one neighbor, sometimes it's not very good. So there's a technique called K-nearest neighbors, where instead of taking one neighbor, I'll take a set of K neighbors. And then some are in this class, some are in that class. I'll do a vote. Majority here are gray, so I'll say that's gray. That's K-nearest neighbors. Very simple. Make sense? We can also have weighted K-nearest neighbors where you can have different weights, and there are some complications, but this is the high-level description of how it works. Now, decision trees, another technique. It does exactly the same thing. I have an object that hasn't been labeled, and I want to label it. How do I create my model? Well, here's an example. This is my behavior, for example. It's not my behavior. It was from another paper. This is Ross Quinlan. So this is a log recording when I will play tennis, and when I will not play tennis. Okay? And these are the conditions of the world. The outlook, the temperature, whether it's humid or not, and whether it's windy. And from this observation of the world in all these cases, I want to build a model such that when I have a new day with new conditions, predict whether I will play or will not play. So we can build something like this. This is called a decision tree. So you can see that if the outlook is sunny, well, I can't decide based on this. I have to check whether it's humid or not. So if the humidity is high, I will not play. If the outlook is sunny and humidity is normal, then I will play in all these cases. In all these cases, if the outlook is overcast, then I will play, regardless of the other conditions. Okay? And this is very similar to what doctors also do when they have cases. Do you have temperature? Is he vomiting? Is he whatever? And you follow the path of the decision tree. The question is, how do I build this decision tree? Is that unique? It's not unique. I can take the same data and create another decision tree. Here I started with outlook, but if I could have asked this, the first question, is it windy? Okay? And then it'll create a different path and a different tree. So the question is, how do I build this? And the learning is about an automatic technique that traverses this data and creates this automatically, and that becomes, so this is the cloud. What I represented as a cloud is this. This is the knowledge that it learns from the data. Okay? So there are recursive algorithms that grow through this data and try to separate it. So in the beginning you have only one node. This is called a node in the tree. You have only one node in the tree, and you start splitting it such that the records in, so the original node has all the data, and so you split it such that the records in a node are all from the same class, or from mainly from one class. Okay, and to split it, you have to select one attribute, and you check the values of that attribute, and then you split it. Now, how do you select the best attribute? There are also techniques to do that, and they're based on how much information does it have to best separate the classes. I won't go into the details, but basically that's the idea. The third idea that I mentioned is neural networks. So neural networks, they said it's based on how the brain functions, but actually it's based on what we thought the brain functions. The only real analogy is the neuron. In our brain, we have actually many types of neurons in our body, actually not just in the brain. We have even neurons in our guts. We have different kinds of neurons. We estimate the number of these neurons at 100 billion. And in addition to the neurons, each one has many connections. Okay. And what happens is that the neuron gets messages from the synapses, from the dendrites, and at one point the neuron fires, and it goes through the axon, and it goes to all the neurons that are connected to it. Okay? And that's what is simulated in neural networks. Here I'm trying to compare the terms of speed or connections. It doesn't really matter much. So basically what you have in an artificial neural network, you have a set of neurons that represent the input. So I can pass that learning, I mean the records that have been labeled, I will pass them in there. And then you have a set of neurons on the outside giving you the prediction, so the label that you should give to the new record. And in the middle you have what we call hidden neurons. And they're all connected. This represents the neuron, and these represents the dendrite. No, actually the axon in this case, but the dendrite of this one. So this one is the synapses, basically. And at one point, this one will fire, and it'll pass it to the next level. Okay? That's the idea. The information is passed as a vector coming in the input layer, and it's propagated one layer at a time to the output until you get the answer. The analogy with the real biological cell is the following. So you have a cell that takes the sum of all the connections, the signals that are coming from the dendrites, the synapses here. And at one point, so these are the different connections coming in. Each one has a signal with some weight. And the soma, so the cell may have its own bias here, and at one point it'll decide, thanks to a function, to fire. Okay, send a message through the axon, and all the other cells connected to it will get activated. So these connections have weights originally, and learning consists of adjusting these weights and adjust also the bias. There are techniques of learning that also sever connections and add connections. Those are a little bit more complicated. But in general, the idea is to change these weights. And the learning, basically, the cloud that I represented, it's the network with new weights. The knowledge are the weights. Okay, that's what we are learning. Okay? I'm going to skip this. So basically how you learn, you have data that has been labeled. I will hide the label. I'll pass all these features in the input. They're propagated. When they come out here, it should be the label. I'll compare this label with the actual that I received. If there is a difference, then I will adjust the weights backwards. This is called backpropagation. Okay. There are many advantages to artificial neural networks. They predict accurately in general. They're robust to noise and so forth. But they have problems. They take a long time to learn. They're difficult to understand. Once you create that cloud, it's actually black box. Okay? So you can't very easily add knowledge. When you had these decision trees, you can adjust them. You can put your knowledge in there. This one, you can't. Also, designing the network, how many layers, what's the size of each layer, it's an art more than in science. It's very complicated, so trial and error kind of thing. If you have it too small, then it will not learn. If you have it too big, then it overfits the data, so it will have poor performance. And deep learning will inherit all these advantages and disadvantages. So what is deep learning? Well, I told you symbol networks typically have a input layer, hidden layers, and output layers. And in each neuron, you get different signals. You sum them up, and you fire. Typically, in a neural network, you have only one hidden layer. You don't have many, because the computers we had in the past didn't have the capacity to put many nodes and many connections. Today, with the new computers, you can add many layers. So it becomes deep. That's why we call it deep learning. It has many layers. Of course, it's a little bit more complicated than that. Now we have many different architectures. There's what we call the simple DNN, the deep neural networks, but there we have also convolutional neural networks, where you have different layers or different parts of the layers that are specializing in different subparts of the input. There's what we call recurrent neural networks, where you have the output of a neural network is actually going as an input for the next one and so forth. This is used, for example, when you have sequences. You take a sequence of words in French and you learn to generate the sequence of words in English. Oh, you have a translator. Okay, so translators work using that. So that's what deep learning is all about. Okay? Why is it so successful? Why now? Why everybody's talking about deep learning? Yes?
Are you trying to like recapitulate how like the neural processing works in humans and like artificially like make that happen and like this learning and like deep learning in these neural networks? Is are we trying to like make it similar or just adapt what happens physiologically?
It's not me first. Not really. This is based on some assumptions we had in the 50s. We know at a high level that, yeah, it works like that, but it's way more complicated than that. This is a simplification of what happens really in the brain.
Yeah, because I was going to say, because like, you know, you have the excitatory and you have inhibitory.
Oh, yeah, we have them also here.
Space.
No, there is also inhibition and excitement as well.
Oh, there is.
Yeah,
okay,
yeah,
I
there is.
Just one
No. You can also inhibit. The neuron can decide to not send a signal.
Depending on the signal.
Yes, yeah. Here I'm explaining at a very high level.
Okay,
Yeah.
interesting.
So why now? Why it's successful? You had a question?
No, it was just a comment.
Comment, okay, good. Neural networks, as I said, existed for a long time. And people were interested in the beginning, and then they turned towards something else that was better, support vector machines. But with new computers, with the power of new computers, we were able now to have way more complicated architectures. And this is thanks to work done by Canadians in Toronto, like Jeff Hinton, in Montreal, like Joshua Bengio. And they tried their techniques on a lot of data in a company that has a lot of processing power, in particular Google. And they were able to recognize images of cats originally, but now they do it in many different things, better than humans. And that was a surprise. Oh my gosh, how does it work? And then they try this on other things, like speech recognition. And speech recognition, this is a slide from Microsoft. There was a competition started by DARPA years ago where they had a data set, a switchboard called switchboard data set. You have utterances of people on the phone and you try to automatically get the caption. What are they saying? And it's extremely difficult. Humans have 6% error rate. The computers were very bad. So for many years, people worked on it until they gave up. Said it's too hard for us, it's impossible. And then suddenly they say, okay, let's try neural networks. And boom, we do better than humans. It's a shock. Everybody was surprised. Oh my gosh, deep learning is interesting. So they tried on many different things. Again, translation. Machine translation, since the advent of neural networks, well, deep learning, the accuracy went up significantly. This is in the case of Chinese to English. The improvements are surprising everybody, and that's why everybody's talking about deep learning. It's in many tasks we're now doing better than humans. Okay, so any questions so far? Because you're going to leave. I want to talk. Yeah, I'm going to talk about some examples of applications that use machine learning, and they're amazingly successful. Yes.
Okay, so I don't know if I'm. If this is a thing, but I think I heard something about like they obviously had like the thing that recognized cats or whatever. Yeah. But then I heard about someone talking about making that for like human faces as well, or just pictures in general, and like how. I guess my question, like with cats, it's a little different, and I'd say it's easier to identify based on like the facial, like the recognition of like the shape and like potential angles you can have it at. But for like human pictures with like different like lighting backgrounds. Yeah,
you can't use the same neural network that learn about on cats to recognize something else. And the features are not necessarily the same. Yeah. That the features that you use to recognize a cat, even you as a human, and to recognize faces of humans are not necessarily the same.
Yeah, but I guess like I think I was having a conversation with someone and just like so it like using because like there's some pictures out there that people take that we can have like a very dark background, so the face is like barely visible kind of thing. Yeah. Still a face, and it like to say for example was to identify like skin tone or like male female kind of thing. Like has that been like created? Just out of curiosity, has that been created or? Do you know of anything else?
There's a difference between recognizing the face and recognizing it is a face. Recognizing which face is it Mr. John Doe or Mr. X? Is it just a face? Recognizing is it just a face? It's feasible, and the neural networks are actually better than humans. Recognizing who is it, that's still an open problem. There are many solutions. People have published solutions, but they're not bulletproof.
Biometrics and security as well with that.
They are used, for example, at the airport or in different places to recognize people. Are they perfect? They're certainly faster than humans to recognize people in a large database. They're not better than humans when it's one picture and I can recognize one person. I can go in a crowd and from the side recognize somebody that I haven't seen since I was a kid. Computers can't do that yet. You need to have full face. That's why they say remove the glasses, shave, and have a white background, and again, will they get you or not? But we're getting there. Yeah. Yes.
Yeah. So when I first heard about neural networking, it was in fourth year neuroscience class, and without dropping the name of that professor. Well, I mean, I obviously got it that it was a joke, perhaps, but he was essentially claiming that this because the course was learning and memory, and it was essentially a cell biology / biochemistry course that was taught by psychology, and so he was saying that like a lot of the recent advances was due to breakthroughs in how they understood how learning and memory as a result of how these neurons and patterns that they fire, the signal transductions and things like that. And from those data results, you guys are able to come up with new algorithms. So my question would be though, obviously that's just a very small understanding of neuroscience and how our brain works. So, and potential algorithms that you could actually develop from that would be dependent on our understanding and further breakthroughs into how it works. So would that would definitely speed up or even
if we knew how the brain functions, it'll change completely the story. We don't know.
But even like another breakthrough, because just understanding how our brain learns was not...
That's why I said in the first lecture that AI is not just for computer scientists. You have even anthropologists, philosophers, neuroscientists also interested because it'll help them also understand their own field. I think AI is helping us better understand, or forces us to focus on some aspect of our brain to better understand how the brain functions. Here, for example, the learning are these weights that I'm learning. We call them parameters. But the brain learns by just changing the amount of chemicals that it's exchanging on the synapses, or the strength of these. We don't know. How do I memorize a smell? How do I memorize the face of a person in my brain? We still don't understand how it works. We know the functions of areas of the brain because they're more active when I do this activity or whatever. But how it happens, we don't know it yet. This is a simplification of what we thought was, in the 50s, how the brain functions. We know that the brain continuously creates new connections. We don't create new neurons. In some cases we do. Here, knowledge is not really represented by new connections. There are very sophisticated algorithms that create new connections and sever new old connections. But the structure of the network is actually built ahead of time. Then you learn these weights. It's not how the brain functions. So again, it's a simplification. The more we know about the brain, the real brain, the more we'll add new ideas in there and probably will improve. But we don't know it yet. It's a lie to ourselves if we believe and claim that this is how the brain functions. That's not how the brain functions. Okay. So here's some achievements. Autonomous vehicles. We have cars that can not just park themselves, but they can move from one place on the East Coast to another place in the West Coast, okay, without driving it. It uses machine learning. How it uses machine learning? Well, it uses machine learning to recognize signs. Is it a stop sign? Is it a non-parking sign? Is it so these are the labels. I give them enough pictures of these signs, and it'll learn what is a stop sign, what is a no parking or no one way or whatever. That's an example of a use of machine learning, but I use machine learning to recognize also pedestrians who's crossing. Is it actually a pedestrian crossing or a plastic bag flying in front of me? Okay, should I brake or not? So there are a collection of machine learning techniques used within that to recognize different things. Yes?
If these machines are supposed to like adapt, would it be able to like differentiate between like a twig that fell over and like blocked the road versus like a giant tree? Like how would it know how to respond accordingly? Like
they adapt not, so there is adaptation because they continuously learn, but it's not just one car that learns. Is all the cars driving at the same time in the history of the self-driving cars, collectively they build a model. So the model continuously improves indeed.
So it really draws its power from big data.
Yeah, exactly, yeah. Another example that you are already using and you don't know is handwriting recognition. For example, the envelopes that have an address that you send to the post office, it's not a human being reading that address, the postal code. I can't read millions of these letters coming in. So there is an OCR that is happening, so I take these characters, transform them into letters, and then I have to recognize them, okay? Different ways of writing the 2, different ways of writing the 3. Is it a B or is it a 6 or is it, what is it? So we have a machine learning technique that learns to recognize these, okay? And it's not just the letters, now it's so sophisticated that you can write even mathematical formulae and it's transformed into written math formulae, okay? These exist in many tabs and phones and not just the post office, okay? It's commonplace. Spam filters. Any email client that you're using will have a spam filter that is also based on machine learning. It learns from your behavior to recognize this is spam, this is non-spam, and adapts to you. Credit fraud detection, I mentioned that. Financial applications, when you have transactions that are happening, is it fraudulent or not fraudulent? Is it something that I should raise a flag to ask the regulators to investigate or not, and so forth. Recommender systems, you all use recommender systems, whether it's for Netflix, for movies, or for books you're buying, or for music you want to hear, or whatever. All these are learning from your behavior and the behavior of your friends, and then recommend something to you. There are adaptive interfaces. I mentioned Facebook, how it adapts to you, the interface, those are the news feeds will adapt to your behavior, the past behavior. There may even remote controls for TV. It learns the channels that you like to see, so when you skip from one to the other, it'll actually jump many channels that you never look, okay? Because it observed how you did that. And if you have many members of the family, there are different buttons. I'm A, so it recognizes A. I'm B, it recognizes B, and so forth. And they use machine learning. There are sophisticated interfaces now for people, paraplegic, for example, on a wheelchair. I cannot use my keyboard, or I can't use my hand to turn the wheelchair. Then there's a hat here with connectors, and it can read my brain activity, the signals from there. And I can think, for example, to move my toe. I'm not moving my toe, but just thinking about moving my toe, I have this signal that I'm sending, and I learn, so the machine learning algorithm will learn that that means turn left. So to turning right, I try to move my finger, for example, and it turns right. Now suddenly, by just thinking, I can send commands to my wheelchair to move forward. And these are used, for example, in the military. You have the firefighter, not firefighter, I mean a military in the airplane. He wants to do different things. He has his hands using something, his feet doing something, but he can think about other commands in the helmet. And anyways, all these are using these adaptive interfaces. They adapt to me, and they use machine learning. Here's some examples in health. So you all heard of precision medicine or personalized medicine. Machine learning is key for that. Often we think about genetics. That's how I personalize, but it goes beyond genetics. But here's an example that uses genetics. So I have a patient was detected with breast cancer. We do chemotherapy, and then we have to decide what adjuvant treatment to give for hormonal therapy. And when we do the biopsy, we can do DNA microarray analysis. We look at the gene expressions of different patients. And we did their analysis before to know if there are estrogen receptor, yes, no. Okay. So we can take all that data and build a classifier such that given a new patient, use the microarray data, and I can tell you if she's ER positive or negative. And that will tell me, should I use tamoxifen, yes or no, for example. And the techniques using microarray data and machine learning is way more precise than the current techniques that we're using. So using microarray data or SNPs, single nucleotide polymorphisms, so these are the mutations in the genes, can be used to build classifiers to predict who will develop breast cancer, for example, or predict who will have breast cancer that recur. So will it relapse after a certain time or something like that. You can also predict whether this patient who's going to receive a kidney transplant, will they reject it or not. You can also predict whether this patient will have muscle mass loss because they have cancer, so decaxia or not. For prostate cancer, you can predict whether a patient treated with radiotherapy will have this toxicity level or that toxicity level or that toxicity level. So this is, for example, the case of prostate cancer. You have different patients that have been treated with radiotherapy. You can look at the toxicity level that they had. Well, 0 means they had nothing, 1 is vomiting, discomfort, and so forth, 5 is death. So they're ranked like that. And the idea is I can use those patients to learn a model. Here are my cloud again. And then when I have a new patient, that classifier will tell me it's low toxicity or high toxicity, not necessarily individual ones, but just high or low. And as a doctor, I can say, oh, low toxicity, then it's worth it to do that treatment. High toxicity, no, I'll do something else because I'm not improving their quality of life. Okay? This is how I can build a decision support system. And again, it's with machine learning. So machine learning is not just with genetics. Here's an example where I'm using just images, and I mentioned that before. So I have images that have been labeled. This has cancer, this doesn't have cancer, so this is a mammogram in this case. And then we learn, based on those labeled data, to predict where's the region of interest. And we help the radiologist, hey, focus on this area, so focus on this area. So we build tools that will help them. We're not replacing them necessarily, but actually we have now techniques that do better than radiologists. But this is the case where we're trying to help them out. Here's another case. This is in collaboration with the Cross Cancer Institute. So before surgery, this is a patient with brain cancer. We want to predict how the cancer will actually develop. Because typically when they do, so this is for radiotherapy, they want to bombard them with X-ray. They don't just bombard the cancer cells, they bombard, I think, 2 centimeters around it so that cancer doesn't come back. But then you kill healthy cells. And killing healthy cells meaning you're attacking some functions of that brain. So if you know how actually it's going to grow, then maybe you will attack 3 centimeters here and 0.5 centimeter on the other side. Okay. Here's another case where, so how do you learn this? You learn it from past patients. Here's another case. I'm not using genetic at all. This is for surgery, for brain cancer. Before you do surgery, you do segmentation in volumes of these scans. And the doctor spends about 30 minutes to do that. It's a long time. And it's a tedious kind of job. So what we do, we learn from past segmentations. And you do the segmentation automatically. You present it to the doctor to adjust it. And they spend 5 minutes adjusting it rather than spending 30 minutes. Okay? So you learn from past segmentations. Yeah, these are the examples that I have. And I want to give you some time to ask me questions. And you can leave now. Thank you for your attention, and please, let's start a discussion.
Do you have any questions about your lecture? Was this your last lecture?
Yes, it is.
So would you prefer if we just emailed you, or if we have any questions?
You can email me. I'll send the slides too.
Oh, you will? Okay.
Yeah.
Thanks again. Sorry I had to leave everything.
I hope you learned something.
Absolutely.
You stayed. I told you.
Wouldn't want to miss this one, that's for sure. And have a good weekend, everyone.
Thank you.
You too.
So, questions?
I would like to be able to use, because I took bioinformatics with Dr. Wishart just down the hall.
Yes.
So we were introduced to some neural networking in that class, just the concept of it.
Yes.
And then we did a lot of microarray analysis, and having done bioinformatics and was in genetics for a while there, it sucks having to do, sorry, wrong language, that's okay.
By the way, you can use also metabolomics.
Yes.
For the prediction. So you can
absolutely, but that's
you can learn from patients that have a disease, and you can look at the urine test sample, and you can learn based on what you find there what kind of disease they may have, and what kind of treatment may work, and things like that. So you can use also that for precision medicine.
Absolutely, because I mean they're all pathways. And,
yeah.
I lost my train of thought. Accessibility to being able to use at least the algorithms, we're learning how to use these algorithms would benefit, I think, like even grad students.
Oh, definitely, but that's why I'm presenting this to you, so you know it exists and you can dig deeper.
Yes.
Yeah, not knowing they exist is a big hurdle already.
How difficult is it to pick it up, though?
Not that difficult. And there are also off-the-shelf tools that have them ready for you. You just have to have a little knowledge of programming or no programming whatsoever. There are free tools where you can try them, but often you need to adjust parameters or adjust even part of the algorithm for the specific data set that you have. But at least using the existing algorithms, implementations of these algorithms as is, with the default parameters, can give you an idea about what kind of accuracy you can get.
I see, yeah. Because without, to be honest with you, I have taken I took one programming class, and essentially what it has taught me was that like programming and coming up with the algorithms is actually the hardest part.
Yeah.
The language itself is not that difficult. The mathematics wasn't that difficult. It was really the algorithm coming up with a really good.
That's the secret sauce.
Yeah. It's very.
But then that like integrates like the math into it. That can be complicated when you.
Yeah.
Because I haven't taken a programming class like in university, but I mean, like in high school, just basic C++, terrible language, but I mean, like the most fundamental one there is, to my knowledge. But yeah, I thought it'd be a lot harder to pick up.
So what I tell most students who are from outside computer science, tell them that a few decades ago, somebody who didn't know how to read and write wasn't the end of the world. If they had a skill, they can work and make enough money to live. Today, not knowing how to read and write is a problem. You need to read and write to find a decent job. Knowing how to program or use a computer is not a big deal. But some years from now, not knowing how to communicate with a computer by programming it will be a big deal. You have to learn.
Yeah, exactly.
So for me as a non-scientist trying to take it in, one of my difficulties is understanding and learning systems when you've got a simple model, simple reward and punishment. But the minute you start putting second and third and fourth and 10th variables, it strikes me that the complexity gets infinite.
Yeah.
So you managed to present this all to us without any advanced mathematics.
Yes.
But
that's the purpose.
But I'm wondering what is the role as you're really trying to build useful learning systems for advanced math? And to give us the full lecture, would you start having to put stuff on the board?
That slide that I used to introduce reinforcement learning summarizes what students learn in a semester. So if I need to go deeper with the details, it'll take longer, and you would need more background in math to follow what is happening. It's definitely more complicated because even the agents that we have today, they don't just learn to maximize the reward for this action. Sometimes actually it may lose in this first action with a goal to maximize it down the road, which is a little bit more complicated. And the math behind it is not trivial to explain. But it doesn't mean to use it, you need to have that knowledge and you need to become an expert in reinforcement learning. There are many packages that exist already that you can use as is. Same thing with deep learning. You don't need to know the details. You can use them as is in these. There's a panoply of these packages. You need to know a little bit of programming, basic programming, whether it is Python or another language, and you can go ahead and use it. So many people believe that, oh my gosh, this is hard. I have to know all this background knowledge. It's not the case.
So you guys are essentially already creating black boxes, programs already packaged for user. Okay.
Yes.
That's good.
The other to kind of go on your point of like the algorithm being like the hardest thing to model, like I'm just like with a basic example of like reinforcement learning that I forgot Patrick was it?
Patrick Pilarski,
he taught us and he showed us like that the like the system that he had set up to get for like for the computer essentially to get from point A to point B with like all these hurdles to get through and stuff. So like algorithm, like coding, like the algorithm specifically is like one challenge, but what about like defining and like setting the environment altogether? I thought like that would be like a whole, like a giant challenge of its own. Like obviously in the case that he gave us where it's just like a 6x6 or a 10x10 square or something like that, and certain certain units are just blocked off altogether, it's relatively simple. But when it comes to more like advanced machine learning, setting up the environment,
it's the same thing. So when you had a maze, and you have an agent that is a square, right. What are the actions that it can do?
Well, for that it's obviously just movements. Like it's simple movements being one up.
Yeah. So the actions is left, move forward, right, move forward. So always move forward, or straight move forward, or down. So you have to turn first and then move.
That's right.
The goal is to reach an XY coordinate.
That's right.
Okay. Now I have a different problem. It's not a maze. It's not an agent that is moving. The agent is an arm.
Yeah, exactly.
Okay. The world I'm in is this room, and my goal is to pick up that.
Yeah.
Okay. And I want to pick it, not like.
Obviously, it's a smooth motion.
I want a smooth motion. Yeah. Okay. So I give the reward when I get there as fast as possible. Yeah. So to get there as fast as possible, as I'm moving, I'm preparing my fingers. I'm opening my fist to grab it rather than doing this. And so basically, you have to define first what are the possible. I show them as tools. What are the possible actions that I can have? And as the world changes, the set of tools that I have can change as well. Yeah. I wasn't able to do this, but now that the state changed, I have a new tool, for example. Yeah. You have to first start defining your goal and defining the set of tools. Yeah. And some actions are more expensive than others. That's right. Expensive in energy, expensive in many, whatever you define expensive. And basically your goal, again, is to reach there and maximize the reward.
What about like when it comes to just defining the environment, right? So obviously you have like certain tools that you can use, like as like your arm, for example, on its own, right? But the way that it not only resides, but how the environment acts on it, and how it acts on like the environment, is that like it's like I'm just like a curiosity. How much more difficult is it to put that?
Well, each problem is different. So I have a robot that can move, and I have a robot that is fixed. It's an arm that is fixed. I can't change it. So depending upon the problem, you have to define that environment and define the actions that you can take. This robot doesn't have wheels. Cannot move from here.
So
it has these constraints. The actions that it can do is depending upon how many degrees of freedom you have and how you can turn, and these are the actions that I can do.
It requires a lot of imagination.
Yes.
You got to be able to imagine it, otherwise.
So I can imagine another environment using reinforcement learning. Patient who has diabetes, type 1. He has to inject himself with insulin 4 times a day. That is based on what they plan to eat and the activity that they will have and the current level of glucose in the blood. Typically what they do, they have this regimen and they write it down on a journal, in a log, and once every 3 months they go to the doctor looks at it and sees the fluctuation, whatever, and they say, oh, add 1 unit here or reduce 1 unit, and then they do it again every 3 months. It's not the ideal case. Okay, you can have a reinforcement learning that learns based on previous measures that you did and previous injections that you did to recommend to you what is the ideal number of units that you should inject yourself. Then that's another completely different. It's not an agent in a maze. Yeah. It's not a robot with an arm or moving with wheels. The agent is this recommender recommending to you how many units to get. And if it gives you the right number of units, it gets a reward. So with time, it learns to give you the right thing.
You know, modern insulin pumps do that?
Not that I know of. They intend to do that. Currently, they still use rules. It's rule-based. It doesn't adapt. but we are working on making them adaptable.
So essentially, you know, I didn't really like the term, the colloquial term that with the AI. I don't really particularly.
You don't like the videotaping?
Well, no. I just don't particularly think we're at the point where they should be using artificial intelligence to define this. And I've had this conversation.
To define us?
No, to define this. To me, it's not elegant enough. Although it is a major breakthrough, and it's more elegant than anything else we've ever come up with in terms of what we could do with these electronics and computing power, right? But it's nowhere near the elegance that we wanted to achieve, which, you know, to an extent, maybe we don't want it to reach.
What is the elegance that we want to achieve?
Well, like,
having us.
Because right now, like, but adaptability is really kind of the tool that we.
I'm calling AI as a set of tools that we build to extend our capabilities.
Right.
One day, that tool, if it learns itself how to improve itself, theoretically, it can become as us.
Yes.
But the elegance, does it have to have our elegance? We are a very complicated machine. We have emotions, we have feelings, and the decision what action to take may be dependent on our feelings and our emotions. These machines don't have emotions. We also make a decision, then we rationalize that decision. Computers know, they use they ration about the decision to take before. We're a completely different beast. I don't think, even if we build intelligent machines, it doesn't mean that they are actually a copy of us. And not because they're not a copy of us that they're not intelligent, and they could be more intelligent than us.
Isn't that part of the problem with the Turing test? That, I mean, it's basically setting the parameter that once a machine can effectively deceive us, that's the standard. But it doesn't necessarily mean that it's in fact intelligent. It just means that it seems intelligent to a certain observer.
I don't know if you remember the example that I gave you for the test to beat humans in Jeopardy with Watson. It's not really a test, but it's a program, the IBM Watson. I tried to open the box to show you the details inside, and it removes the magic. But from the outside, it appears that it is intelligent, but it's not necessarily intelligent. So what is intelligence from a machine? It's still a big question mark. It reads these words. Does it make sense of these words? It doesn't understand what Mozart is. Remember that example with Mozart and symphony. Doesn't know what a symphony is. Doesn't know what last means. It's the last one. Has no understanding of these words. Yet it can get you the answer better than humans. Will we get machines that will finally understand what it means? Symphony is actually music, and it's classical music, and who is Mozart and all that stuff. Some people believe yes. But some people believe that we don't need to really understand the details behind it to be intelligent. They're different schools.
Different way of defining things, I guess, and classifying things. Right?
I gave you a different definition of intelligence than you heard on Tuesday. But which one is right, which one is wrong, doesn't mean one has to be right. Both can be right.
I mean, I guess just particularly because of because of movies, fiction, and things like that. Essentially what I'm trying to get at is much bigger than just the science. Well, I'm just saying that, like, it's over the negative connotation that it had prior to the resurgence of it now is confusing the public. And most people that are not familiar with, don't really understand how the algorithms and the coding works.
Yes.
Right? So in many ways that's going to be bad because it affects policy. I mean, hype is good, but hype could also be bad. Right?
That is true.
Affects policies, and as long as humans are still where around like emotion-based decision making is going to factor in.
Have you seen the movie Her?
Her?
Yeah, when the guy got, well, he fell in love with the agent that talks to him on the phone. And he was disappointed when he learned that that same agent was talking to other people, millions of people at the same time. And for some people, they also were in love with her and stuff like that. That's science fiction, but it exists already today. We have agents that communicate with millions of people at the same time. There's a particular agent called Xiao Ois in China. And the purpose is to become friends. And when you are good friends, then it can start recommending products for you to buy, because you trust a friend, you don't trust somebody else. And so what happens is that if you ask it a question, and you have this open-ended kind of conversation, but if you ask it a question, it cannot respond by generating a response that makes sense, because it doesn't know the meaning of these questions. What it does, it asks that question to one of the people that it is communicating with right now. There are millions of people. And it gets the answer, and that's the answer that it gives to you. And it seems, wow, it is amazingly smart. But actually, it's a human that did that. So it's again the appearance of intelligence, not
it's the magic that you talked about.
Yes.
Really
when you open the box and see the magic, then it's not magic anymore. And then it's not AI anymore. And that's why AI is a moving target. What used to be, take the example of finding the best path from this place to that place. That was a tough problem. Yes. Today on any smartphone, you click, boom, you get the answer. It's not a big deal anymore. So it's not AI.
Yeah.
And many things are like that. So yeah, you do. You do.
Use an Apple phone.
Yeah.
That's probably why.
Yeah. But we humans are the ultimate intelligent machines, and yet we give wrong answers too. So wrong answer doesn't mean it's not intelligent.
Wait, so like the whole like algorithm set up with like Google Maps and like, well, like if you set yourself to like leave at a specific time of day kind of thing, that is all AI. Is that like, well, okay.
It doesn't necessarily, not all these algorithms are using what we call AI,
right.
but,
so, but yeah, that's what I was going to ask. Is that like incorporating some parts of AI, or is it more of like their immediate data collection that they have because they know how many phone users they have?
No, they use a lot of AI too, but not everything is using AI. Okay. It depends upon the appearance on the outside. It's like what I showed you, the example for Watson. That example that I showed you is just information retrieval. There's no AI in it, but it looks on the outside. It is AI. It's intelligent. So Google uses a lot of AI. They adapt to you in a way you can't imagine. They know more about you than you remember about yourself.
That's true. But is Google Maps AI though?
No, they don't necessarily use AI there.
I mean, it's also just, it hasn't gotten to that point where if you plot 15 like for example, it has to decide between 15 destinations before you reach your shortest. Before it reaches your destination, like for example, if you plot your route across a small neighborhood, you're going to be stopping at one street, at another street. It's going to take, it's a traveling salesman problem.
But it can use AI if, for example, you always take the scenic route.
Yeah.
Next time you ask for a route, it'll give you the scenic route because that's what you want. Yeah. Okay? Well, thank you.
Thank you very much. Okay, well.